Welcome to Brain Vision.
This is chapter 27, problem number 38. We're given a current, downward current, and the B field that this current carrying wire is exposed to changes directionally in part A and B and C. And we are to calculate the magnitude and the direction of the magnetic force acting on this current carrying wire under different conditions. So first of all, the current is given to us as, so if this is north, this is south, the current is given to us as it's downward, so it's into the board, right? This is the direction of the current. And now in part A, we assume that the direction of the magnetic field is towards east. So this would be our east, this would be our west. So if the direction of the magnetic field is towards east, then when we're calculating the magnetic force, as you know, ILB sine theta, this theta being the angle between I and B. In this case, you clearly see that they're 90 degrees apart, right? Sine 90 is going to give us 1, so that the force is going to be equal to I times L times B, simply, in this case. Magnitude-wise, we can do the calculation because I is given to us as 2.6 and L is 1 centimeter, so let's convert that to meters. And then we have the magnitude of the magnetic field, 5.588 Tesla. And then if we do the calculation from here, we're getting a small force, newtons. Now let's look at the direction of this force. From the right-hand rule, if we align our thumb with the direction of the current, and then the rest of our fingers along the direction of the magnetic field, and curve our fingers 90 degrees, that would show us the direction of the magnetic force. So if we do this, as you can see, the direction of the magnetic force is going to be along the south. So FB is towards south. Now, part B. Again, we have the direction of the current into the board, right, into the screen. In part B, the direction of the magnetic field is given to us as towards south. So this is the direction of B. Again, let's calculate the magnitude of the magnetic force applied on the current carrying wire, ILB sine theta. Again, the angle between I and B is going to be 90 degrees, so then sine 90 is going to give us 1. Then if we're going to plug in the same values and we're going to get the same magnitude, right? However, the direction of the force is going to change this time. Again, using the right-hand rule, we conclude that FB is towards west, right? Now, in part C, what we're given is actually, again, the direction of the current does not change, but this time, imagine that this is east and this is west. The magnetic field, the direction of the magnetic field is given to us as 30 degrees south of west. So it looks, the direction of B looks like this. By the way, this is the 30-degree angle, right? So then when we do the calculation in order to calculate the magnitude of the magnetic field, actually we're going to get pretty much the same answer. The reason for that is still I is perpendicular to B, sine 90 is going to give us 1, and I times L times B is going to give us 0.015 newtons. However, when it comes to the direction of F sub B, we're going to have to use the right-hand rule. Remember, your thumb is aligned with the direction of the current, and then the rest of the fingers are going to be aligned with the direction of the B field. And then we're going to curl our fingers 90 degrees. So if we curl our fingers 90 degrees, 30 from here to there, and then another 60. So then this is going to be total 90 degrees, right? So then this is going to be the direction of the magnetic force in this case. So you can say F sub B is 60 degrees north of west.